And thanks very much to the organizers for going to the great effort of bringing us all here. Non-trivial task. So I want to start in a biblical fashion here. I guess I don't need to shout with this thing on. I want to start in a biblical fashion. So, in the beginning, God created four infinite families of simple, complex Lie algebras, which man has named AN, BN, CN, and DN, and 5 exceptional simple complex Lie algebras. Which have become known as E6, E7, E8, F4, and G2. And this biblical epic sense here, I'm only partly joking. This is, as many of you already know, this is an amazing list of objects which were just given to us, and they're just there. And in particular, in Lie theory, we were much luckier than the number theory people who were given a terrible list of prime numbers to study. For us, we have this very simple classification of our elemental objects, and you can spend your entire life, several lifetimes, studying these things. They come up everywhere, as you know, in geometry and algebraic geometry and representation theory, harmonic analysis, physics, all over the place. And there are also many, many different things you can do with these, which again just come out naturally. D modules, perverse sheaves, spring varieties, all sorts of fantastic things. And one of the many things you can do with these, which just pops out naturally, is quantization. And so that's going to be the goal here, is to understand what quantization of these God-given objects looks like. I'm going to take, again, quantization is an enormous thing. You could spend your entire life studying different versions of quantization. I'm going to take a very operator algebraic point of view on what quantization means. And because we only have 3 times 50 minutes, unfortunately, I can't really talk about all of them. I mean, we'd be here all week if I wanted to do that. So I had to make a choice. My choice has been that I'm only going to talk about the very first of these objects, A1. And then I'm going to tell you that all the others have analogues of increasing complexity, but from everything that I'm going to talk about in the 3 lectures here, everything is known in generality, but there are many open questions just next door which are unknown even once you get away from A1, even once you get to A2, for instance. There are still a lot of things in the quantum world that are extremely unclear. Okay, so let me just start by reminding you the origin story here. So maybe I'll do it over here. So a Lie group is a manifold, smooth manifold G with a smooth group law. Okay, and as an example, we could take a matrix Lie group, which is a closed subgroup, G contained in, that's me making that noise, isn't it? Maybe I'll do that. Let's see the problem. Is that better? Maybe that's better. Okay, G contained in GLNC inside MNC. Full stop. The eagle-eyed amongst you will have noticed that nowhere in this did I demand that it be a submanifold. It's merely topologically closed, and this is part of the God-given nature of Lie groups, that they come to us for free with their Lie group structure. Just the fact that it's a topologically closed subgroup is already enough through a bit of work. It's not very difficult, but through a bit of work, you can already show that this it has a God-given smooth structure, and so that it has a Lie group structure, just like that. This is going to sort of be a recurring theme, sort of indication that these semi-simple, simple Lie groups can be produced in various different ways, which all amount to the same thing. Okay? You could give various different definitions, and they all turn out to be the same or closely related. Of course, manifolds are hard. We would be much happier with a linear space. So the first thing we do, of course, is linearize by taking the tangent space of the identity element, which comes equipped with its Lie bracket. Which is the derivative of conjugation. More than that, I will not say. This is not a course on Lie groups. And in particular, if it's a matrix Lie group, the bracket, well, so first of all, G will be in be a linear subset of matrices, and the bracket of two such matrices is just the commutator. But now I've made my life better. I've moved from manifolds to linear spaces. Unfortunately, these are real linear spaces, which are not great. They're better than nothing, but I'd much rather have a complex linear space. So then I will define the complexification of this guy to be the usual thing. And so with the complex numbers. So if you like, this is just my original Lie algebra plus another copy of the Lie algebra with a formal I in front of it. And I extend the Lie bracket by complex linearity to get now a complex vector space with a complex bilinear Lie bracket. Okay, so that's better again, but it's not an associative algebra. It satisfies the Jacobi identity. I'd be really happy if I had a complex associative algebra. So that's the last thing we're going to do. So this is the universal enveloping algebra. It's the universal associative algebra with an embedding of this Lie algebra like this, such that Lie bracket of two elements is this guy here, and this is in the associative algebra. Okay, and again, I could give you a much more formal definition of what this guy is. Many of you already know. And again, this is not a course on Lie algebras or Lie groups, so I won't do this. I'll just pass immediately to our basic example of A1, write down explicitly what this algebra is, and then we can start working with it. Okay, so all of that is just forward, like I say, the origin story in this world where our guys come from. I'm also not going to tell you what simple or semi-simple means. Apologize for that. So, fundamental example. My group will be SO3, which I'll call K because it's compact. So this is the underlying group of any physical system that has rotational symmetry. Then my K, Lie algebra, of course, is just written in a different font. And as many of you probably know, it happens to be isomorphic to SU2, which is a set of all matrices, 2 by 2 matrices, such that it's skew adjoint and its trace is 0. If you've never seen this before, that again is for another course, but I'm happy to talk about it after the lecture. But I prefer to go make a beeline for the objects of interest. Okay, then our complexified guy, which I'll start to call G, is, well, it's K plus IK. So these are the skew adjoint guys, these are the self-adjoint guys. Any matrix could be uniquely decomposed as a skew adjoint plus a self-adjoint. So this is all matrices subject to condition they have trace 0. So this is matrices, 2 by 2 complex matrices with trace 0. We have a basis for these guys, which is the most important basis in the history of the universe. That's trace 0. That's trace 0. That's trace 0. And every trace 0 matrix is in the span of these 3 guys. Okay, so now if I want to have my universal associative algebra with an embedding of these guys, I'm just going to take non-commutative polynomials in these 3 basis elements. But of course, I need it to satisfy this. So I'm going to impose that the commutator in this associative algebra is the same thing as the commutator as matrices. Okay, so we need to just check how the commutator as matrices works. This, again, probably many of you already know this extremely well, but it's worth writing down explicitly. Up to flip, these are all the possible Lie brackets of basis elements that are non-trivial. So that's all we need to know. And then our UQG, or UQKC is maybe better, is the algebra generated by the 3 elements H, E, and F, satisfying these 3 relations. Where these 3 relations should be taken as now commutator brackets. Okay, so HE minus EF is 2E, and so on and so forth. Yeah. Oh, thank you. I got ahead of myself. Yeah, that looks better. Okay. Thank you very much. Getting too excited. But indeed, this is the great moment because now we get to the 1980s. And in the 1980s, so the representation here of this classical algebra was known extremely well. In the 1980s, physicists, particularly Russian physicists, started discovering representations of something that looked just like this algebra, except that it had some Q polynomials floating around in it. And so again, God made their presence known by manifesting some new property of this algebra, or some relative of it, which was quickly, in a matter of several years, discovered to apply to any of the simple complex Lie algebras that I mentioned at the start of the lecture. So to say what the Russians uncovered, I need to quickly tell you what a Q number is. So digression. Q numbers. So I'll take a complex number, A, and the Q number AQ is this guy here, Q to the power of A minus Q to the power of minus A over Q minus Q. Right, so in particular, if, oh, I didn't say what Q was. Well, maybe I will, so you could take Q to be a formal parameter or something like that. But let's actually take Q to be in 0 infinity. 1 is going to cause a problem, so I'll be dividing by 0, but not for long. But this is what an operator algebraist can consider, Q in this range here. You could take, if you're an algebraist, you could take Q being any complex number, maybe not 0. And that will be totally fine. But let's stick in the operator algebra world where we want Q to be a positive ring. So in particular, if A is an integer, and this is a polynomial, and I have this famous identity, let's say it's a positive integer, just to be safe, then I get Q to the A minus 1 plus Q to the A minus 3, all the way down to Q to the A minus A plus 1. And if I'm not mistaken, that makes A terms. And now that's perfectly well defined when Q equals 1, and I just get A. Okay, so some remarks. The first is that if I put Q equals 1 in this limiting sense, then I get back my usual numbers. So they're somehow deformations of standard complex numbers. The other thing is that they behave a little like usual numbers. For instance, I have this identity here, just to mention one. If I do A minus B, Q, A plus B, Q, I get AQ squared minus BQ squared, which is kind of cute. You want a warm-up exercise and you've never done that before, you can check that out. And there are various other quadratic relations that look just like the usual quadratic relations for the Q numbers. So they're obviously A plus B Q is not the same as AQ plus BQ. This is not a linear map. But somehow they behave quadratically a little bit like the normal numbers. It's just the way they. Okay, so now back to the groups. So they were working on quantum scattering theory and things like this, coming from problems in solving matrix equations, from quantum physics. which I'm completely ignorant. They discovered these guys and gave them to the mathematicians. Well, that was sort of a heritage, God passed them to them, and then they passed it to us. And it looks like this. So here's the first one. UQ of SL2 is still generated by the same guys, but with a quantum version of these relations here. And the quantum version of these relations here looks like maybe I'll do it to the side. It's like that. This guy here needs some discussion, because it's not just a polynomial in H, it's a transcendental function of H. And an algebraist is not allowed to do this, at least not straight away. I'm going to give you 3 different ways of understanding that. The first is an algebraist's way. Use formal power series in log Q. So that means you can write this guy, which of course is supposed to be Q to the power of H minus Q to the power of minus H over Q minus Q inverse. Q to the power of H you can write as exponential of little h times big H, which is now expandable as a formal power series in little h. That means I'll no longer be in this algebra, which is just polynomials, but I'll be in infinite polynomials in these 3 generators under the condition that the powers of H go to infinity. So this is called an H-adic completion. We're not going to talk about it, but I give it to you as a little present. The second version, which is my favorite, it's a little bit awkward for certain reasons, is to use functional calculus. But that requires me represent E, F, and H on Hilbert space, let's say, with H being maybe a self-adjoint or at least a normal operator be even nicer if I can represent it on a finite dimensional space, then it's just taking matrix exponentials. Matrix exponentials are very nice. That's the second way I could do this. Like I said, it's the way I'll mainly concentrate on. The third way is to avoid the question by change the generators by putting Q to the H as a generator and forgetting about H altogether. I don't like that because H is much nicer than K. But okay, it's a good way of doing it as well. And to understand what that would mean, you need to do the following exercise, that if you have H and X, which are matrices, then if you have this relation that commutator of H and X is lambda times X, then you have the following exponential commutation relation. Okay, so this linear commutation relation is equivalent more or less to this exponential commutation relation. So what I could do is replace my three with a different color. Replace my generator H by generator K, which I'm going to demand be invertible. So let's also throw in its inverse as a generator. And I will require that, what will it be? Q to the power of K, E, K inverse B, Q squared E, K, F, K inverse B, Q minus 2 F. And now this guy makes perfect sense. That's another very popular way of doing things. And I'm sort of going to jump a bit between versions 2 and 3. So this is a perfectly nice algebra that was not just, invented by man, it was given by God. And it behooves us as a species to understand the representation theory, right? I don't say that every human needs to work on this, but some humans need to work on this problem and understand why this algebra is there and what its representations are. Okay, so that's now our job. That's what I propose to do today. In the 20 minutes remaining, a bit more, 25? I don't remember what time I'm. Okay, the next 15 minus epsilon minutes, we'll do the representation theory of this algebra. And then in the following lectures, we'll discuss why it deserves to be called a quantum group. I mean, it sort of came from a group, but it's now a very distant cousin to a group. So we'll talk about Hopf algebras, so on tomorrow. And then we'll talk about not the complex version, but the not the compact version, but the complex non-compact version on Friday. Sorry, it won't be tomorrow, it'll be Wednesday, and then non-compact on Friday. That's the plan. Okay, let's make our life easier by talking about finite dimensional to begin with. And let's begin with a remark on the classical situation. So every finite dimensional representation of the classical guy. So I'm thinking of SL2 here. Whenever I write G, I'm just being lazy. It's always SL2. Though, of course, again, there are analogs in higher rank as well. Has H acting diagonally with real spectrum. It's not totally obvious, but it's true. And so as a place to start, it's maybe a good idea that we consider these kinds of representations. So that means that Q to the H a representation now of its quantum cousin. Called integrable, as a hangover from the world of classical representations where they integrate to representations of the group, or sometimes class 1, if you follow Klimek and Schmidtgen. If Q acts diagonally, sorry, if Q to the H, excuse me, acts diagonally with positive spectrum, strictly positive spectrum. If I have such a representation, my life is immediately easier because in that situation, I can take a logarithm, an operator-valued logarithm or a matrix-valued logarithm. And so that means instead of working with the K, which I've already said I am biased against, I can work with its differential variant, H, which is going to be much nicer. So now the theory. So firstly, part of the theorem, which I won't mention, every finite dimensional representation of this algebra UQG decomposes as a direct sum of irreducibles. This is called complete reducibility. It's the same thing for its classical cousins. That just means that I don't have to worry about the way in which different irreducible representations are combined. They're just combined by taking direct sums. And then every irreducible, finite dimensional, integrable representation of the algebra UQG is isomorphic to one of the following. So they're indexed by either integers or half integers, depending on your personal preference. I'm going to take half integers. The vector space on which it acts is going to be 2m plus 1 dimensional. And it's going to be spanned by vectors which I'll call Vm, Vm minus 1, down to V minus m. If I've counted right, that is exactly 2m plus 1 elements. And H will act on V mu by 2 mu V mu. This is why you have to make a choice whether you want to use integers or half integers. Because I'm using half integers, I need to multiply my eigenvalues by 2. It's just different indexing. F of mu will be mu minus V mu minus 1. And E V mu will be V mu plus 1 up to some constant. And if I'm not mistaken, the constant is m minus mu quantum m plus mu plus 1. Okay. Some notation terminology. An eigenvector V of H is called a weight vector. With weight equals half, again, because of my chosen conventions, the eigenvalue. So that these guys are all a basis of weight vectors of differing weights. This guy here is a weight lowering operator. And this guy here, E, is a weight raising. In that it sends a weight vector to a vector of strictly larger weight in the following sense. Okay, no, in the sense that is given here. I think I'm good. Any questions on the statement? Good. Oops. So there's two parts of the proof. There's, of course, the existence, but that's just check relations. And then there's uniqueness. And that's the part that I want to concentrate on. So suppose we have one of these representations. I can take, as I said, the logarithm of k to get the action of h. So h has a bunch of eigenvalues, has at least one. What I'm going to do is take m to be, so let v be such an irreducible representation. I will put m to be the weight that is half the eigenvalue of h of.
So the way you formulated this more integral because you have h, you have a, right? So the hypothesis is that the h is semi-simple is important, right?
Yeah, so I'm cheating. I've definitely missed out. I'm totally cheating. I've missed out a part of the proof, which is to say that this this is a reasonable hypothesis to make. But if I impose, yeah, so I have imposed integrable. I'm not lying. I'm cheating, but I'm not lying. Yeah. I'm allowing. So of course I should write k of v mu is equal to q to the power of 2 mu times v mu. Then I wouldn't be cheating. But I will allow myself to write the action of its logarithm, its q logarithm. I agree. Yeah, absolutely. But I don't like these nonlinear things here. I don't like it. But there's nothing wrong with it. It's totally fun.
No, you needed the diagonalizable of k. Am I right?
You absolutely need the diagonalizable of k. But, well, let me write the next part and then I'll explain why I'm biased. So it's a personal bias. I agree with this. You could write everything in terms of powers of q. But I have a personal bias because it simplifies the writing of certain formulas. So I'm going to take the weight of highest real part. Okay. Now I'm even permitting myself to get slightly out of the world of integral representations. If it's integrable, it is real by imposition. But let's imagine that k is just diagonalizable, not necessarily diagonalizable with positive spectrum. And that I simply assume that k can be written as q to the power of h for some h. And again, I'll have to get back to why that's a reasonable assumption to make, but certainly in the case of integrable, this is a reasonable thing to consider. Okay. And now what I have is an extremely important fact. Which is that if V has weight lambda, then what happens if I do H of, let's go with FV, now let's go with EV. So this is HEV plus EHV. So this is, that's 2 times EV, that's lambda times EV. So I get, or rather 2 lambda times EV, so this is 2 lambda plus 1 times EV. So that is to say EV is again a weight vector, but now with weight 1 larger. That is the most important fact about QSL2. And we see straight away that E in any one of these representations is automatically acting as a weight raising operator. Likewise, if I did exactly the same calculation for F, I would find that it's acting as a weight lowering operator, lowering the weight by 1. I need to do better than that. Consequence being that the set Vm minus 1, Vm minus 2, etc., where I'm putting Vm minus k to be Fk Vm, is invariant. I need to take its span under, firstly, H, because it's just acting on these as eigenvectors. Secondly, F, by definition, but also E. Thanks to the following little exercise, which you can amuse yourself with later if you're bored, is that if you take commutator of E with f to the power of k, you get kq times f to the k minus 1 times, and certain people in the audience are not going to like this. What is it? H minus k plus 1. I'm going to double check that. That's exactly correct. Where this, of course, should be written as a q power of h. So you could write that in terms of k's, and you could rewrite this lemma in terms of K on the right-hand side. I haven't used H at all on the left-hand side, so there I don't need to change anything, but I could rewrite the right-hand side in terms of K, and it would be more correct. It's still correct once I've represented where H is the matrix logarithm of K. So it's not false in this context. But you'll probably more often see the analogous thing with K's. So the result of this is that if I hit one of my FKVs with E, I can pass the E past it, in which case, and I forgot to mention that EVM is 0 because VM has the highest weight. So if I look at EVM, it has higher weight and therefore must be 0. So now, if I move my E past, I'll have E times VM, which is 0, and then I'll have this guy, which is some multiple of VM hit with FK minus 1, so it's just VK minus 1, so it's a weight raising operator. I had better stop soon. So in any case, what we see as a consequence of that is that EFKV is this guy here, so it's KQ. And then this guy here acts on VM as M minus K plus 1Q, Fk minus 1V. And this is exactly the formula here, where I replace mu equals M minus K. This is as in statement if mu equals M minus K. So it looks like I've proven it. I've got exactly these formulas. The only thing is that this looks like an infinite dimensional span. So of course, I'm supposed to be considering only finite dimensional guys. So eventually this is going to be 0. Let's look at the first one that's not 0. This formula still applies. So this formula still applies. So if this guy is 0, but this guy is non-zero, then one of these terms must be 0. Can't be this one, because K is a positive number. So it must be this one. Oh, and that should be 2n, I just realized. Because of my conventions. So since finite dimensional, I must have Fk Vm equals 0 for some K. So 2m minus K plus 1Q is going to be equal to 0. I would like to say that means that K is that 2m plus 1 is K. Okay, so that 2m plus 1 is an integer, which will give me exactly what I want. Turns out that you can have 0 Q numbers which don't come from 0 numbers. I'm going to, I think this is right. These are the guys that give 0 Q numbers. They're purely imaginary. So the only one that is real, the only one that gives me an integrable representation, if you like, will be 0. But if I allow myself to stray away from the integrable guys into the complex world, then I pick up some extra finite dimensionals because of this strange phenomenon of the Q numbers. So this explains why often in the world of quantum groups, you get some bonus representations that have no classical analog. It's because of the behavior of these Q numbers, having some periodicity in the imaginary direction. So I've proven my theorem. By lack of time, let me just put a square. So in particular, if n is real, then m is k minus, what is it, k minus 1 over 2 with k in n cross. So I get exactly my representations from the theorem. But I've also picked up some bonus ones, which are exactly the same dimension, but with some complex part. And let me just to finish, if I may say no, let me just finish by saying this magic word. The following guy is called a Verma module. So now I'll assume these guys to be all non-zero. So I'm constructing something, I'm imposing a new infinite dimensional vector space, not finite dimensional anymore, with representation of UQ SL2 given by the formulas of the theorem. So same H acts as eigenvalue, acts on these as eigenvectors, F as weight lowering, and E as weight raising, with exactly these coefficients here for the E weight raising operators, even if they're going to be zero, just occasionally. And then what I get, and here I really will stop, is, so let's call this a theorem to finish with. If M is not a half positive integer plus one of these guys here, then this guy here is irreducible because this coefficient is never zero. And if else, I get actually an inclusion this guy here being generated by exactly the one that has a coefficient 0 before it. So it will generate an irreducible submodule V minus M minus 1. This is my Verma module with quotient being the finite dimensional guy here. So that I just wanted to say you can realize these finite dimensional guys as some cohomological object related to some infinite dimensional representations. And the advantage of these infinite dimensional representations is that they can be extended continuously for any parameter, not discretely like these guys here, which need half integer weights. Yeah, so this is supposed to be pi H inverse integers. Right? Thank you. So for the rare integer values or half integer values here, modulo some periodicity in the imaginary direction, I get some decomposability, reducibility in these Verma modules, which are exactly our finite dimensional guys and the best. Thank you. Sorry? It jumps by 2 if I take the different convention where the M is the actual eigenvalue. I've taken M to be half the eigenvalue. And so it does, the eigenvalues jump by 2, you're right. But in my convention, the M. Okay.
Well, two points. Firstly, you were looking to relate to
yeah.
But this is
extremely interesting.
I really love that presentation, very effective in but I think the thing with your meeting information got And it seems to me that we can set. And so that would correspond to U vector SL zero, no completely like the zero. Now there is an inductive construction which categorical nature, they simply mechanically or highlighting the construction will get the one instance. So there is a deeper origin in my view.
Okay, no, it's the Big Bang then. That's, yeah, okay.